Hey, hi everyone. Good morning.
Good morning, Shrikant. Shrikant, just one or two queries I have.
Sure, good.
So one was that, when we are doing that label encoding, so
Mm-hmm.
it doesn't go in the ascending order. It just randomly assigns anything. Am I correct? I mean, we cannot force it to, it was like like BP was low, normal, and high. So
Right.
it doesn't assign low as 0 or normal as 1 and high as 2. So I remember, I think it
Uh,
was rather low as
yeah,
1, normal as 2, and high is 0.
yeah. Basically, it's taken alphabetical order. Um,
Oh,
so,
acha.
or else you can explicitly hard code and label that as however you want. But randomly, it takes alphabetical order.
Oh, okay. Okay. So it's by alphabetical order.
Yes, yeah.
Okay. We can
Okay.
hard code
But
it.
however, you can also use that replace function, and you can replace low with 0, and then medium with 1, and then high with 2.
Okay,
But in
okay.
decision trees, it doesn't matter, if even if it's randomly assigned the numbers, because there we are not giving any weightage to a category, right? So
Okay.
in that way, it's fine.
And I mean,
Okay.
that post pruning
Hmm.
concept was still not, I mean, I was not able to grasp it because that output was an array over there. What, I mean, you were saying that,
Oh, okay.
just can you
So
take
those
maybe a
are
few minutes? Can you just explain that once again from that Python one, in the Python code? Because you said the info gain is less than so and so number, but it was an array. So how do we I mean, decide which
right.
number it is going by?
Let me open up that then. Any other question apart from that? I'm just opening up my Jupyter notebook.
Yeah, I think that's the only one I have for myself.
Okay. I hope you can see my screen.
Yes, yes, I think.
Okay. So this is the model name, right? CLF, right? Here we have initialized somewhere on the top here, right? This is
Correct.
a decision tree classifier. So
Yeah,
what we
yeah,
are
yeah.
doing here is in this decision tree classifier only, we have this function known as cost underscore complexity pruning path. And then we are
Okay.
passing this X train and Y train. So what it will do is it will build the entire tree first, okay, and then it will try on various alpha value,
Okay.
okay. So this is the complexity parameter value, okay, which you
Yes,
have seen
yes.
right in the decision tree
Yeah, yeah.
initially in scikit-learn. I talked about that is one of the hyperparameter. This is one of the hyperparameter. What it does is, what they have done is internally it will identify multiple alpha values and calculate the impurities. Impurities, you heard about, like, this is nothing but like kind of an entropy, okay, which it
Yeah,
will
yeah, yeah.
calculate,
Closer to one.
okay.
Yeah.
So, right. So if you say print impurities, then it will print impurities also. Now, at various alpha values, it is calculating the impurities.
Okay.
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 And then these are the these are the alpha values which I am going and using it, okay, one by one as a threshold to prune my tree. Okay, from 0 till 0.0532. And now your question would be, why can't we take it static? It cannot be static because for different tree, the improvement in the entropy could be at a different level, right? So it's always better first you take the model and then train the entire model and then iterate at various alpha values to calculate the impurities. Okay, so you can, even when you print the impurities, you will find out at this particular alpha value what is the impurity overall, at this what is the overall, right? But here I am kind of again training the model separately at each of these alpha values. So what it will do is at every split, okay, at every split, it will see that is the improvement greater than this particular value or not. If the improvement, that means the information gain, if it is greater than this value, then it will allow that branch, otherwise it will not allow. So here we are restricting. You have seen,
Okay.
right? We have given the maximum depth, we have given the
So yeah.
split. So if you pass this hyperparameter,
Okay. So every
okay,
time we are taking a loop of this array. Okay.
yes. So this is the array. This is a different alpha values on which I'm trying, and then I will compare at which
Oh,
alpha
okay,
value I'll
okay.
get a better result,
Okay,
right?
okay. So
So
fine, got
here
it.
I'm doing, and see here this is a graph, right? So basically this is a graph, right? So these are the alpha values. This is the training accuracy, and this is the test accuracy. And we know that why we are going with pruning, because we have, when we have to deal with overfitting, then we have to go and do the pruning. Uh, okay, so earlier when I'm not pruning, so this is the gap between my accuracy and the test accuracy. So after pruning, I'm kind of reducing the gap between my training and test accuracy, and that's how, I'm making this model more generalized, and it would be better model production, okay, for the production uh, deployment. So now with this graph, I understood that somewhere at alpha values closer to 0.02 is giving me a better training accuracy and the test accuracy. And then here I'm using that alpha value, and then I'm training the model.
Got it. Got it. And this
Got it?
chart, what is this?
Uh-huh.
What are those values are given? What is that value? If you go back to the
This
tree,
value
no, no, no. The tree it has created. If you go up, I think where is the tree?
up.
I mean,
Yeah.
yeah, like what is this value like 114 and 36? I'm not able to. What is this picking up?
There is a
Values.
number of
Okay,
observations in each of the groups. So you have two
okay,
classes, right? So 114 is from not heart disease, and 36 are
okay,
from
okay,
heart disease. And this class is the majority class in this particular group. Okay.
okay, okay, okay.
So total sample is 150. This is the
Okay, okay.
split.
No, no, no. Yeah, got it.
114
Yeah,
point
so
one.
total, yeah, splitting that.
Uh,
Okay, fine, got it. Yeah.
all right. So any other questions on this code? Anyone? All right. So if no other questions, then let's move to a different topic today. Yep. So now we are getting into a kind of a black box models, okay, algorithms. Um, High level, we can understand what's happening, what could be happening inside this particular algorithm, but explaining or interpreting this particular model could be difficult. Okay, so in short, this is called as SVM, which stands for Support Vector Machines. Okay, this is the one of the most sophisticated algorithm. If you are aiming for higher accuracy, then you can go with this particular algorithm. But again, there is a trade-off you have to take. So though it will give you a better accuracy, but the explainability part would be very minimal, okay, in this particular algorithm. So let's understand how it works. Okay, so here I'm taking another use case where based on the size of the cell, okay, um, I am classifying, or it's basically a tumor cell. I'm classifying whether the tumor is benign or malignant. Benign means non-cancerous, and malignant means cancerous. So just based on the size, shape, and different other properties of that particular cell, um, we are trying to classify whether that particular cell is cancerous or not. Okay. So here again, so you need to have a historical data which is labeled. And again, this algorithm is a supervised learning algorithm where you need to have a output variable and the input variables both. Okay, so uh, when we give input variables along with the output variable, so that particular process is known as supervised learning, where the model, where the algorithm will learn based on the input and the output, and it will identify the relationship and all those things, patterns, and then that's how it builds the knowledge. So now what is SVM? Okay, so as I mentioned, it's a supervised algorithm. Uh, Basically, at a high level, if you just in a one sentence, if you have to answer about SVM, it classifies categories by finding a separator. So, for example, in n-dimensional space, your data is scattered all throughout. Okay, and now you have to categorize each of the category. Just just think about a kind of a separator which will separate each of those categories, right? So something like this. Sorry, a separator which separate these two categories, something like this. Okay, so it could bring up this kind of a separator, even if it is a multi-class problem. Okay, so for multi-class, it will have a separate separator for between each of the classes. Now you're seeing it is completely non-linear. It is not a straight line which is separating the classes. It can be of any shape, and the good part is like it can map the data to a high dimensional feature space, and then it can very effectively it can find out the separator. Okay, so see, this is how it has identified a separator. Now how it does. Okay, so basically we call the separator as a hyperplane. Just think about something like this. Okay, so you're sitting in a room, right? So your room is a three-dimensional space, right? Where you have a height, length, and width, right? It's a three-dimensional space. Now, if let's suppose you have to divide, you have to bring some kind of a separator inside your room. So how it would be? You cannot just draw a line and separate the room into two parts, right? You need to have some kind of a plane, okay, or some kind of a sheet, which you can put it so that you can divide your room. So the line basically is used when it is a two-dimensional data, right? So if just on the floor, if you have to divide the room, then you can draw a line. If on the wall you have to divide your wall into two parts, then you can draw a line. But if inside the room, the whole exact room, if you have to divide, then you have to put a sheet, right? So that is nothing but a plane. So I'm talking in a three-dimensional space, it looks like that. Imagine just if you have six-dimensional or 10-dimensional or 20 or 100 dimensions. Okay, so that means you have 100 input features. So what it does is it maps that data to that high dimensional feature space. If you have even 20, 30, 100 features, so in that high dimensional feature space, it will find a separator. So that separator, we call it as a hyperplane. Hyperplane means at the high dimensional space, whatever plane, it builds, that called as hyperplane. Okay, so now let's suppose this is your data. This data looks like this. Now to separate this data, so these are the blue ones and these are the red ones. Okay, so if you want to separate the data, your separator should look like this, something like this, right? Okay, so it should be a U-shaped kind of a separator which can separate these two lines. Now, what it does is now it is a non-linear separator, right? It's a not linearly separable data. So in this case, now you can relate it to the logistic regression also. In the logistic regression, what we did is we kind of use a linear line to predict the two classes, but it didn't work. So what we did is we changed that um to a non-linear form, right? So that my output should range between 0 and 1, and based on the probability, I can able to find out. So I did some kind of a transformation there to fit to my particular use case, or to so that I can get results the way I want, right? I want it between the range of 0 and 1. So here also, what happens is here some transformation will be done on the data so that a data which is not linearly separable get converted into a linearly separable form. Because see, to find out the line like this, like non-linear line or the lining something like this, is not possible by it's not possible algorithmically. Okay, so what they have done is they chosen some other path where based on certain transformation, you can convert the data which is not linearly separable to a linearly separable form. So see, now this was X. Okay. Now what they have done is they have made some kind of a transformation. They have added one more column as X square. And if you use these two columns, now your data would look like this. So we call it as a quadratic transformation. Okay. If you take cube, then it is even higher non-linear form. So we call it as a polynomial transformation. So here, when you convert a particular variable into a higher degree, okay, so your data would get converted from a non-linearly separable to a linearly separable. So now if I have to separate this particular data, now I can use a linear line to separate these two classes. Okay, so this is the major um, task of this SVM. So whatever data you have, it could be non-linear separable. So there are certain transformations which you can apply on using this SVM, which will convert this not linearly separable to a linearly separable. Then after that, once it is a linearly separable data, now we'll see that how it will identify this particular plane, okay, which we call as a maximum margin hyperplane. In short, we call as MMH. Okay, so let's understand how it works. Okay, so these are the transformations. Okay, so you need not to bother about the transformations. So there are certain kernels. Okay, we call as a data transformation kernels. So we have a linear kernel, we have a polynomial kernel, we have a radial basis function, radial basis function. In short, we call it as RBF. And then we also have sigmoid. So sigmoid, you know about it, like in the logistic regression, how we are using a sigmoid, which we call as a logit function, and transforming the data into a nonlinear form, right? So so these are the kernels available in SVM, and this kernels are also called as hyperparameters for this SVM. We can use these kernels and see which kernel is working better on my data and through which kernel I'm getting a better accuracy. So what linear will do is it will not do any kind of a transformation. So the data, the way it is, okay, it will try to find out the linear separator. Polynomial, as I mentioned, okay, it will try to use a higher degree polynomial variables to see that whether your data has been changed into a linearly separable. So to whatever degree, at whatever degree, this data gets transformed into a linear separable. So that level of transformation it will do, and then SVM will go and find out the uh, this particular hyperplane. Okay, so I'll take one example. Okay, so now, not this, one second. So let me switch to other presentations. So there I have some example for you. Hmm, Now see, let's suppose this is your data, okay, where here, if you have to divide these two classes, the green one and the blue ones, it's not a linearly separable. You cannot have just one straight line which can divide these two categories. You need to have some kind of a circle like this. Now, this would be your hyperplane, which can divide these two categories, um, properly. So now, how can this particular kind of hyperplane um, can be identified? So for that, let's what it will do is SVM, it will try to transform this data so that it can become a linearly separable. So now currently this data has been plotted between X and Y. So now a new variable will be calculated, which is Z equal to X square plus Y square. Okay. Now what happens is, now if this particular data has, if it is plotted between X and Z, now the data would look like this. Okay, so this is the beauty of this feature engineering and the transformation. Okay, earlier when the data has been plotted between X and Y, so data was not linearly separable. Now it is linearly separable. Now you can have a line like this, which can easily segregate these two classes. Now that is known as best hyperplane, right? So this is now, what is this transformation known as? This transformation is known as radial basis function, RBF, because radial means a circular, right? So now you cannot view the data first of all because you have more number of features in it. You cannot view and you cannot decide which kernel to be used. So it is just a trial and error. So whatever kernels are available, you just try one after the another and see that which kernel is giving you the best results. Now, once the kernel is decided, okay, now yeah, the same hyperplane, which is a straight line between X and Z. If you plot that hyperplane between X and Y, it will look like this. Okay, this hyperplane. But to detect this hyperplane, the data has to be converted into a linear form, linearly separable form, and then only you can able to get this kind of hyperplane. Okay, so now let's see, how basically, this SVM would work. Okay. Now let's suppose it is a linearly separable data. What do you think? Which particular line is a good separator? Is it A or is it B? We have two lines here, and both the lines are separating the data, right? Both the categories. So but what do you think? Which one would be a better separator, A or B? Anyone? Which one would you choose?
B looks better.
B looks better, yes. Yes is better, but why do you think it's better?
I mean, both kind of data is like equidistance from this
Hmm.
line, like that linear regression we have that.
Yeah, in the linear regression, the point has to be closer to the line, right? But
Yeah,
now,
but
yeah,
it's
but
almost
now, huh.
equidistance.
Now is it good to have a points closer to the line here in this case, or it would be good if the points are far from this line? See, for this line, the points are closer, but for this line, the points are far from this particular line. So yeah, B is the right answer, but I want to understand, and that's the same logic, this SVM would use, to find out this particular line. So just think about it, why you think B is better? See, unconsciously, you said the answer, right? So B is the right answer. But now logically think, why you think B is a good separator? Just think about it. All right. So see, it's simple, right? See, now this point is very close to this particular line. Let's suppose if I add small variance to this, okay, if there could be some noise added to this particular observation, it will get misclassified. It will fall in this particular zone, right? So this particular line is has a very less cushion of variance, okay, to handle the variance, right? So with a small variance, it may lead to a misclassification here. So if you are like, if you have two classes, something like this, and you take a line which is very close to these points, okay, so it is a very tight and very close separator, right? The boundary is very close to this observation, and in if the little variance in the values uh, um, is seen, then it will misclassify those observations. So here we do not have that much um what you say space to handle the variance, right? But here we have enough space, right? Even if there is some variance get added, even if these points are like falling here, still, the good amount of space is there on either side to handle the variance. So there's the reason what this SVM will do is it will try to find out that line which has the maximum margin. So what is that maximum margin? So this is considered as the maximum margin. So the distance on the either side, as you mentioned, from this line has to be maximized. So that's how, again, there would be an optimization algorithm which will try to find out a line which is giving me the maximum margin. So that's the reason this optimal hyperplane is called as maximum margin hyperplane. Now, how it finds? So see, now I'm just taking example of two categories. So there is a complex geometric and quadratic equation which works behind the scenes to come up with this kind of optimal hyperplane. So just I'll give you the intuition how it works is like firstly it will try to find out the convex hulls. So these are known as convex hulls, the boundaries of each of the categories, convex hulls, right? So it will find out the boundary here also for this particular category. All the uh, observations which are on the boundary are called as support vectors. Now, with this support vector, so these points are nothing but the vectors, right? Because we have multiple values attached to these observations, which are nothing but the coordinates, right? And with that coordinates, we understand the direction and the position of that particular observation. So that's the reason it is known as vector. Now, these vectors will support this particular algorithm to find out the optimal hyperplane. So that's the reason it is called as support vectors. And this entire system, they're calling it as a machine because it is a very sophisticated algorithm. So they're calling it as a machine. So that's how it is named as support vector machine. So now once it is identified this convex hulls, now what it will do is it will find out the distance between every pair of observations which are on the boundary, right? So it will optimize, it will automatically find out, which of the observations are facing towards each other, and then it will find out the minimum. So let's suppose these are the two nearest data points, okay? And it will create the perpendicular bisector, okay, of this particular line. Now that will become the optimal hyperplane. Now before that, what it does is, so whichever uh, uh, vectors which are on the boundary, so passing to that will be the dotted line, which is known as margin. So these you can consider it as the boundary lines, okay, the boundary lines of this particular category and this particular category. So these are nothing but the tangent, okay, which will pass through this boundary. Now, once it is done, now it will find out the nearest two observations and then it will take the perpendicular bisector. So if it will take the perpendicular bisector, it will make sure that it has a equidistance on either side, right? So this particular distance and this particular distance would be equal. So now this is a very ideal scenario, okay, to have this kind of to get this kind of separator. But in the real scenario, you may find certain outliers. So there would be certain exceptions. There should be certain noise. So what if, you have a green color observations here? So there could be a case, right? So this observations, if it finds out the boundary, it will find out the boundary like this. Now, if the additional green color is here, are you following what I'm saying? So let me take a green color. I don't have a green color here. Okay, let me take this color. So I have another observations, which is this green here. Okay, so now the boundary, the convex hulls will be like this, right? Now what will happen? Uh, Now it will find out something like this here. Uh, Here it is not a linearly separable, so let me make it as a linearly separable. Let's start this. Uh, it's not getting erased. Okay, so let's suppose you have one point here, okay, which is your green color. Now the convex hull would be something like this. Now, ideally, what you will do if you have a point like this, if you have to do it manually, what you will do, you will say that let's ignore this, okay? Because if I consider this particular point here, my hyperplane would be something like this. Now see how close it is passing from all these observations, right? So now it is a riskier model. Now this hyperplane is the model here in this case in SVM, right? So maximum margin hyperplane is your model. Now, if I take this model, it is a riskier classifier because if, as I mentioned, if there is a little bit noise added to these observations, okay, it may fall into this particular zone and it will misclassify those observations because there is not enough space for this particular category. Okay, probably for this category, it may classify all correctly, but this category, there could be a chance that it may misclassify. So to avoid that, if you have to take a decision, what you will do is let's ignore this. You will ignore this particular point, and you will say that okay, it's okay. If one particular observation is not getting classified correctly, it's fine. But other 90% of the observations, I can able to predict correctly with this optimal hyperplane. And now this would be more robust model because it has good amount of space on the either side of these categories. So even if there is some kind of a noise added to it, it will do a correct classification. Now this is known as margin, right? Because now this margin will give you some kind of a buffer or some kind of a cushion, to handle the variance. So how to handle that, we will discuss now. So for that also we have yeah, so this is covered. I'll come back to this particular deck again. Okay, so now we were discussing about this kernels. Okay, so kernels will just do the data transformations, and once it converts the data into a linearly separable, now you have seen that it will find out the hyperplane which has a maximum margin. Now, how it can basically avoid those outliers and all. Okay, that's something we will understand now. If you see here now, these are the boundary on the boundary, these are the vectors which found, and based on these vectors, it will identify these margins, and based on that, it will identify this maximum margin hyperplane. See, these are known as support vectors. Now, so there is a equation like this, okay, for this, and there is a equidistance like -1, and this is +1 on both the sides, right? So that's how it will identify the plane. So the advantage of this model is it is give you a very high accuracy on a high dimensional data. It's memory efficient. The way they have programmed this particular algorithms, it algorithm is that it does not take a lot of memory, so that's the reason it is fast and quick, and it will give you a better accuracy. So disadvantage is like as you see that it can overfit. Okay, if you don't use certain hyperparameters, it may overfit. So as I mentioned, if there is a noise also, it what it will do is if you do not use any parameters and allow this model to come up with a hyperplane, it may come up with a plane which clearly distinct the two categories. So you will get 100% accuracy on your training, right? But on the test, it may not perform good. So it is prone to overfitting. Okay, in that case. So another major disadvantage is you cannot do the probability estimation because it is just a linearly separable. It will just tell whether the observation falling on that side or this side. So it will just classify. So probability estimation cannot be done on this. On the smaller data set, generally we don't use because it is a highly sophisticated model. So generally the time it takes, to process, to train the model is almost on the smaller data set. Also, it will take some some time, to come up with a model. So generally, we consider this model when we have a high dimensional data and where we are too much concerned about the accuracy, right? So in that case, SVM is the best model. So now the SVM can also be used in the image recognition. So for that, the image data has to be converted into a numeric format, and then you can differentiate what is this image, whether it is a dog or whether it is a cat, whether it is a cycle or whether it is a car. So you can categorize multiple objects, okay, in the images through this particular SVM algorithm. Text category assignments, even in the NLP side, you can do it, like detecting spam, generating sentiment analysis, the gene expression, so all high dimensional data. If you talk about image, again, it's a high dimensional data. Text, definitely, okay, it's going to be high dimensional data because you are going to deal with lot of different words, right? Even the genes data in life sciences is again high dimensional data. So this SVM basically is the algorithm when you have to deal with larger data sets and you are aiming for a better accuracy, then you can go with SVM. Now let's see, how basically, yes, how basically this outliers are kind of dealt, right? So if you see, we have this red points and this green points, okay? But there are certain outliers. So there could be certain exceptions everywhere, right? Let's suppose a person with a lesser age may earn a higher salary, right? So that's an exception. If you want to deal, if you want to classify the salary based on the age, there could be certain exceptions. Okay, so your model has to be your algorithm needs to be so intelligent that it should identify those outliers and it should able to ignore those outliers, okay, while learning, because this may create a confusion and it may lead to a model which may be a overfitted model, right? So here in this case, this green is kind of closer to this particular category, and this red is closer to this green category. So if I consider these 2 points in each of the categories, now my hyperplane may pass something like this, or it should come something like this, right? So which is not a good model, though it may give me 100% accuracy on the training data on which I'm training this model. So it will identify the hyperplane like this, but in future, if I'm putting any new data onto it, So if there is a little bit variance here, the green, this particular observation, it may be misclassified. So that's the problem you may have, when there are certain outliers. So what it does is there is a certain parameters known as epsilon. Okay, it is denoted like this, and there is a cost function. So epsilon, just think about it. Epsilon is uh, like a good teacher or a soft teacher, which allows the students to do some kind of cheating, right? So here this particular epsilon is allowing this algorithm, to ignore certain outliers. Okay, but this is a strict teacher now. Now what it is doing is it is penalizing on every misclassification. So for example, for this margin, okay, if it takes this particular margin, now this is the misclassification because it is falling on that side, right? This is also a misclassification falling on this side. So as epsilon is allowing this algorithm to do misclassification. Now this cost function is calculating there how many misclassifications are done, okay, by this algorithm. And that's where these two parameters would work together and there would be a trade-off at which, with a minimal misclassification, how this overall model is giving me a better accuracy. Okay, so cost function is nothing but your accuracy. It will get reduced, when there is some misclassifications. So yeah, see about it. So here I am putting a higher cost, saying for every misclassification, 100 is the penalty. So if that's the case, it will not do any kind of uh, misclassifications. Even, it will allow points to be on the margin only. Okay, it will not allow even these points to get inside the margin. Okay, so this would be completely uh, blank. Okay, if the cost is high. Okay, it will not allow any observations to even to cross the margins. Now, if it gets little liberal, okay, so the cost is 3 now. Now you see that some of the observations it will even allow, to fall inside the margin. So these observations will not be considered while calculating this maximum margin hyperplane. Only these are the support vectors which are falling on these margins will be considered to come up with this maximum margin hyperplane. So even if you go further down the cost function, even it will allow some of the observations to fall on the other side also. Okay, even it will allow some misclassification to happen. So how you can set is, there is this epsilon, okay, where you can allow this epsilon that's saying that it should, I'm putting that epsilon less than equal to -1, okay. So what it will do is, this is your -1, this is your +1, okay. So it will allow these observations to even get into this space, okay. If you say, greater than -1, then it will even allow, the observations to fall on the other side of the margin. Okay, so like that, you can use the epsilon and the epsilon will allow to whatever, extent you specify the epsilon, based on that, the observations will fall on the other side. And the cost function on the other side, it will keep a note like how many misclassifications are happening. Okay, and based on that cost, if the cost is higher, then there would be a bigger impact on the overall accuracy. Okay, in that case, it will control the number of misclassifications and it will come up with a hyperplane with a minimal misclassification so that out of 100, at least 90% or 85% of the observations are classified correctly with that particular hyperplane. So bit tricky. Okay, so you need not to bother about it because in Python, there is a simple function. Okay, you need to just use the parameters and it will able to give you the better model. So you just need to use these kernels. It's just a hit and trial kind of a thing. kernel you change and see that which one is giving you the better results. And then this cost function and this epsilon you have to change and see that which one is giving you the better results. And that's how you have to train your model. So again, if I have to quickly recap this particular algorithm, so let me get into this particular slide. Again, you can take the notes. If somebody asks you what is hyper SVM, so it is a supervised learning problem. It can also use for classification and the regression problem. How it will use for regression problem, where we are maximizing the margin here, in this case classification. In the regression problem, it is inverse. It will minimize the margin. Okay. In that case, all the observations will be closer to the line. And that's what we have seen in the regression problem, right? But the most important part of this SVM, which makes it very unique, is that transformation, those kernels. Kernels are the most important part of this SVM, which makes this particular algorithm a special algorithm, because you are converting the non-linearly separable data into a linearly separable. Now, if it is a linearly separable, now it becomes very easy, to deal with, because in mathematics, the linear equation is very easy to identify or to calculate. So it is used for classification as well as for regression, but primarily again it is used for classification problems. But even, as I mentioned, if you have a regression problem, you can try SVM on that also. So the goal is to create the best line or the decision boundary that can segregate the n-dimensional space into classes, so that we can easily put the new data point in the correct category in the future. So it's all about, for example, our states, Indian states, and the countries, how they have been segregated with the boundaries, right? Uh, so the same way, all these categories in the n-dimensional space will be segregated by these boundaries or by these separators, which we call as a hyperplane. So these decision boundaries are called as hyperplane. Okay, so the SVM chooses the extreme points vectors. So these are the support vectors, right? Extreme points means the points which are falling on the boundary of each of the categories. Those are known as extreme points, and those are nothing but the vectors that helps in creating the hyperplane. So as they are supporting in the creation of this hyperplane, so these are called as support vectors. These extreme cases are called support vectors, and hence the algorithm is termed as support vector machine. So I hope at a high level you got the idea just about this algorithm. So it's all about finding out this maximum margin. Okay. So whichever line is giving me so it will find out first of all the margins, right? With this support vector, am I getting the maximum margin, or with this support, let's suppose there is another support vector. If the line passes like this and like this, is it with this whether I will get a maximum margin? So it will identify with which support vector am I getting the maximum margin, then it will find out the nearest ones, and then it will take the perpendicular bisector. So that's how it will calculate this maximum margin hyperplane. So we have a linear kernel. Okay, linear kernel is nothing but, you are assuming the data is a linearly separable and you don't want any kind of a transformation. There you define the kernel as linear. Okay, so used for linearly separable data, which means if a data set can be classified into two classes by using a single straight line, then such data is called as a linearly separable. So by default, it would be linear only. It will consider that the data is linearly separable. Uh, First, you try that, because that is a simpler way of, and it will not take much time, to train the model. If it is giving you the low accuracy, then you change the kernel. If your data is if you are lucky and if your data is a linearly separable, at the first go itself only, you will get a better accuracy. Now, let's suppose you didn't get a good accuracy with a linear kernel, then you apply the non-linear kernel. The non-linear kernels is used for non-linearly separated data. And you have seen, right? We have radial basis function, we have polynomial, we have sigmoid, right? We can use either of these and try and see that which one is giving you the better results. So this is your linear. If the data is linear, then it will identify the the best line, okay, which segregate these two classes. Okay, and it will use the maximum margin hyperplane technique, to come up with that particular line. If it is a non-linear, then what it will do is it will do some transformation based on the kernel which you will decide and give it to this algorithm. So based on that, it will do that kind of transformation. If it is RBF, then this kind of transformation will be done. If it is polynomial, you might have seen, right, in the earlier case, it will add the higher degree variables to the data, and that's how, the data will become linearly separable. Here, it is a polynomial of both the square term of both the variables which got added to your data. Now, if you plot the data with this new variable, it will look like a linearly separable. And on this particular data, it will try to find out the linear hyperplane. And on the original data, your hyperplane will look like this kind of sphere or radial. Okay, and that's the reason it is called as a radial basis function. So that's about SVM. Any questions? And you see that, okay, which variable is important, how it has identified this hyperplane. So it's all computation which is happening behind the scenes, right? Once this particular hyperplane is identified, you can just use it to classify. You cannot able to explain it to somebody. How you will explain this particular model, right? Because it is just a boundary, decision boundary, which it has identified to classify the categories, right? So there is not much of explainability on this particular model. So if any stakeholder is expecting that this model to explain why this model is classifying a particular observation, something into category 1 or category 2, that's something it cannot able to explain. But as I mentioned, if the accuracy is the most important objective, then you should go with SVM. If the explainability is the important objective, then you should go with the simpler models like logistic regression and decision trees and all those things, right? Or the naive Bayes. So any questions? Is it clear? Yes or no? All right. So let's look at this data. Okay. So this is the cancer data again taken from the UCI machine learning repository. Okay, so this is the real data. Okay, so somebody has kind of contributed or uploaded that kind of data. So you can get more information in this particular website. So here is the link. Okay, so the data set contains several hundred human cell sample records. Okay, and what each of the field names are and what does that mean. Okay, so there is a bit explanation around it. Okay, so I'm loading the data here. I'm finding out the count. So here it is important to consider mm, if your output variable is a categorical variable, it's always good to find out what is the proportion of each of the categories. So for example, let's think about it. Okay, I have hundreds of cells, okay, in my cell samples in my historical data. But let's suppose out of 100, only 10 or 5 cells are cancerous samples, but rest of all the cells are non-cancerous samples. So do you think it's the right data to train the model? Of course not, because see, if I'm just passing only the 10 observations of the cancerous samples and 90 samples for non-cancerous, definitely my model would be more biased towards the majority class, right? So that data is called as imbalanced data. So always make sure before training the model, you check your data and see that if your data is an imbalanced data or a balanced data. So generally the imbalanced data you will find where you will have some kind of a rare classes or rare category. So again, another example, for example, machine failure. Machine will not fail very often, right? So some or the other day the machine may fail. So, but the machine would be in a healthy state most of the time. So in your historical data, you will find more observations of the machines at a healthy state when compared to failure cases. So again, when you are taking the historical data, make sure that you have a equal number of observations or they are close. Okay, it should not be completely imbalanced. There should be a balanced proportion of both the classes. Otherwise, what will happen is overall accuracy of the model you may get very good, but if you measure the recall we have seen, right? If you measure the recall, out of actual truths, true true actual positives, the true positives would be low. Okay, so here that's what we are doing here. So this is the output variable. I'm finding out the count. It still it looks like a little bit imbalanced, but not that imbalanced like where I'm getting only very few observations in one class and more observations in another class, right? So this is how my I've just taken the two variables like unit size of the cell and the clump, and this is how my scatter plot looks like. So I have a completely scattered data of malignant and benign. Malignant means cancerous and benign means non-cancerous. Now I'm doing some kind of data pre-processing. What I'm doing is it looks like column indicates some values that are not we can okay. So in some of the columns, there are some non-numerical data. Okay. So with this single line of code, okay, what I'm doing is I'm dropping all those rows which are not numerical. Okay. So again, I'm converting this particular variable into integer. So earlier, this is an object. Okay. Why it has been detected as object? Because there could be certain rows or certain cells in which some non-numerical characters, you know, by some errors or by some typo might have included. So here I'm doing all that cleaning. Okay, so I'm just finding out which all are not numeric, and then I'm dropping those errors, dropping those rows, and then converting that particular variable into integer. Now it is integer 32. So the 3264, I think you guys know about it. Like it's a 32-bit size. Okay. So here again, 32-bit size will take a numerical value up to certain length. Okay. If you have a bigger values you may expect in that particular variable, then you can go with integer 64-bit, right? And that much amount of space it will allocate for each of these variables. Okay, so now this is my all the feature columns or the input columns, converting that into an array. So this is how my data looks like, and this is my output. Now I'm splitting the data here. Now these are my kernels. Okay, so here I'm taking this sklearn. From sklearn import svm. Okay, so directly svm I'm taking. And here I'm taking svm.svc. So this is the entire module, SVM, support vector machine. In that we have SVC and SVR. SVC is support vector classifier. SVR is support vector regressor. Okay. So as it is a classification problem, I'm taking the SVC and the kernel I'm passing it as RBF. Okay. Radial basis function. I'm fitting on my data, then I'm predicting, and then after that I'm doing the evaluation. So let's see, what I'm getting here. Okay, very good. I'm getting around 94% recall, and here it's almost 100% for other category. Okay, so overall F1 score, if I want to calculate, it is coming out to be 0.96. So again, the evaluation and part, I'm not digging too much because it would be the same, right? We have discussed in Naive, we have discussed in logistic regression, we have discussed in yesterday's decision tree classes. Okay, the evaluation part will be the same for all the classification problems. So you can just take that part and run it here, because every time what you have to pass is you have to pass the actuals and the predictions. That's all. So this particular code will be always the same. Now you have to see from where these predictions are coming. It can come from support vector machines, it can come from decision trees, it can come from naive base, it doesn't matter. Okay. So the evaluation part will be standard. Okay, whatever algorithm you are using. Okay, so the plot for plotting this particular plot, I have created one custom function. So you can build this kind of a custom function, so that every time whenever you have to plot a confusion matrix, you can just call this particular function and you can pass the values to it, and then it will build the. So here I'm using it. Okay, I'm passing these all the arguments. Now it is building this kind of confusion matrix. Okay, so the code is simple, right? So see, though the model was so difficult, but here it is quite easy. Okay, so you can just change the kernel. You can just change the kernel and see for which kernel you are getting a better results. Okay, so you can just take it as an exercise and let me know. Okay, is any other kernel gave you the better result than RBF? Okay, and internally, that epsilon and that cost function. So basically, they have set it as a default value, which on an average will give you a better results. But if you explicitly want to go and change those epsilon and cost function, that also you can do. So in scikit-learn documentation, you can go to the page and it will give you an example how you can change the epsilon and the cost function. But typically, by changing the kernel, okay, the kernel is the most important parameter for this SVM. By changing the kernel, it will give you you can get the better results from this SVM. Okay. So anybody has any question, any doubts? So
So
you have to pass.
any fine tuning parameter for this algo?
Sorry?
Any fine tuning parameter
Yeah,
for
this is
this?
kernel. Kernel is your fine-tuning parameter, which we call as hyperparameter. So see,
Okay.
if you use linear, probably it may not give you a better result. So how you tune it? You just change the kernel, change it to RBF. Okay, now you see what is your result. So what is this fine-tuning is all about is you are changing certain parameters to improve the overall accuracy. So here in this case, it's a kernel, which is the most important hyperparameter of SVM. So you can try all these kernels, 4 different kernels, and see which one is giving you the better results, and that's how you can fine tune your model. Clear? All right. So now you have the code for all these algorithms. Take this data set and try other models also on the same data set. That's how you have to practice. Okay, just swap the data, swap the code, okay, and see how you can try different algorithms on different data. I'm not making it too complicated for you, because see, all these algorithms you need not to know in depth. You just need to, at a from a practical perspective, at a high level, you should know where to apply which algorithm, and at a high level, you should understand, how that algorithm works. Okay, because as a data science professionals, we will be using certain tools and platforms to train the model. So we are not going to do anything manually, right? So at a high level, if you understand how this algorithm works, you can choose the right algorithm to solve a particular problem, and that is very, very important, guys. So we called as an applied data science. So you need to learn apply data science to understand how this data science can be applied to solve some real business problems. Okay, that is very important. So I'll just give you one scenario. Yesterday, I was taking one interview. I met with one candidate who has a excellent theoretical knowledge. I when I was talking about transformers, when I was talking about Gen AI, he was like theoretically was explaining me everything, okay, which even I was not aware of. He was talking about attention mechanism and all those things. And when I'm giving the case study, when I'm saying, okay, if this is the case study, how you will solve, that's where he couldn't able to answer. Okay, I said, can you use this particular algorithm or this particular algorithm? His answer was like he started again explaining me both the algorithms, saying that this is algorithm works like this algorithm works like that. I was really impressed by his theoretical knowledge, but the practical experience of applying those algorithms, there he was not that good. So we had to reject them. I was I though I wanted him to hire, but I couldn't because we cannot utilize him as he joins, right? It may take time for him, to pick up, to learn, how to apply those skills in solving some business problems. So please emphasis more on the practical side. See that how can you pick up these algorithms and you can solve the problems. And if somebody is giving you the case study, then talk from that case study perspective also. Don't jump into again on the theoretical part. He wants to understand, like, if you will be given any particular kind of a problem, how you will think about it, how you will basically he wants to check your problem solving skills, how you will solve that particular problem step by step. You have to tell that, okay, I'll take the data, I will understand the data, I'll process the data, I'll do the feature engineering, then I'll select the right algorithm. And here in this case, if the explainability is important, then I will go with this. I'll go with the simpler models. Then that's how you will fine tune that model, how you will evaluate those models. That's something you have to explain. Okay, so that is the most important aspect, guys. Okay, so have both the things, right? Have a good understanding about the algorithm and same time, understand how those algorithms can be practically applied to solve a business problem. And by now you have seen, right? I have taken multiple examples from marketing, from healthcare, from life sciences, right? From telecom. So you have seen the customer churn, customer uh, classifications, and all those things. So, and now you have seen towards the life sciences. From past three classes, we are taking all the life sciences use cases, right? Heart disease prediction, cancer prediction, and all those things. So you see that this particular data science can be applied anywhere, okay, in any domain, any industry, in any function. So the domain understanding is also important. So if you are working in any particular domain, from now onwards, think about it like in your domain, what kind of predictive analytics can you perform, okay, and what kind of scenarios you can use these supervised learning algorithms to do some kind of classification or some kind of numerical prediction, which could help the business. Think from those lines. And if you start thinking from now onwards, so by the end of this course, you can identify some of the projects which you can include in your CV, right? If you have an experience in particular domain, then it's better, include those projects, because in the interview, if somebody asks you certain question related to that particular domain, then you can able to answer. And that again will give you some brownie points. Okay, so prepare, guys. As I mentioned, the three skills which are more important. One is the theory part. Second is the programming part. The third is your domain part. So cover all these things. Okay, it's not just simply whatever I'm explaining here, you're just revising that, but other things also on your own, you have to start building that. Okay, it could be a communication skills, it could be presentation skills, it could be your analytical skills. That also you need to build. I don't know how many of you have covered this SQL. In the beginning of the course only I mentioned, go through SQL. So I don't know how many of you have covered, but please do it. Okay, SQL is an important skill which you need to add in your CV. Okay, so SQL is important. Excel, something, okay, basic Excel you should learn. MS Office like Microsoft Word, Excel, PowerPoint, that skills also is important. Though they will not ask you in the interview, but when once you join any particular role, so for on the day-to-day task, it becomes very important. Okay, so all those skills you need to start building it slowly. Okay. And let me know if you need any guidance, any support, or if you have any query. So please speak out. I don't want you guys, to come on this class and sit silently. So we have time. Just like you guys are not answering questions, so I'm just wrapping up early. But if you have any questions, need to discuss anything, please go ahead and discuss. I can help you out. So any comments, anything you would like to discuss, guys? All right, then perfect. Okay, so I'll share this code. Okay, go through it and let's connect tomorrow. Thank you, guys.